Most programmers spend the first 5 years of their career mastering complexity and the rest of their lives learning simplicity. This quote comes into my head every time I start a new project. And one of the steps of mastering complexity is to find those islands of simplicity within a new challenge. And keeping things simple should be the primary objective of every engineer. I'm Marian Grada, a software engineer at Cognizant Softvision, and in the next 25 minutes, I will highlight some of the benefits of using Kafka streams within Spring Boot context. And then I'll go through an example to demonstrate how easy it is to use it within your projects. My plan is to present the basics of Kafka streams, going through the Kafka topology, K-stream and K-table, stateless and stateful operations. And after that, I will tackle the pros and cons of using Kafka streams with Spring Boot, what Kafka streams offers out of the box for record transformations. And in the end, I think I will cover a scenario within a trading application. I bet many of you have heard of Kafka and Kafka streams, and some of you already use it within various projects. Therefore, I will not make a tutorial from this presentation, and I will focus on the important aspects, so everyone can understand the idea behind the Kafka streams. In the diagram, Kafka streams fits into step number 3. So, what is Kafka streams? Kafka streams is a library used to process data that can be integrated in any application built on top of JVM. And it doesn't need a separate container or a separate cluster to run. Basically, applications that use it can run on any platform. The library offers a domain-specific language that was built on top of Streams Processor API and contains stateful and stateless operations, and we will get into details a bit later. Kafka Streams does all the processing with a latency of milliseconds, and this is the most important part. And with this in mind, I would like to go further and talk about the features of Kafka Streams. What are the best features of Kafka Streams? Well, it's highly scalable, elastic, and fault-tolerant, but what does it actually mean? So as for any consumers in Kafka, the scalability is strictly related to the number of partitions that were set for a topic. And fault tolerance comes from Kafka, from the fact that the data is stored in a reliable way as it is duplicated across replicas. Threading and parallelism. Again, the number of partitions dictates the number of tasks that can run in parallel within the same application. Process one record at a time. This is what gives Kafka streams that edge of processing messages within milliseconds. And the most important one, in my opinion, the exactly once capability, the holy grail in message delivery. And Kafka Stream does this out of the box, of course. It's using transactions behind the scenes. Kafka Streams topology. Well, a processor topology is a graph of streams processors, represented in this diagram by nodes. We can have source processors, we can have stream processors, we can have sink processors that are connected by streams represented by edges. A stream is an ordered, replayable, fault-tolerant sequence of key-value pairs, which are the data records. As you can see in the diagram, a record is read from an input topic, processed within a topology which can create intermediate topics, can create state stores from which we can query records later on, and in the end, writes the transform records to an output topic. This is pretty much how Kafka streams work. So, Kafka streams has two main ways to represent streams, either as a K-table or a K-stream. A K-stream is a record stream that is theoretically infinite, and if I were to draw a parallel with a database, all records are handled as inserts. For example, in this case, if I would like to count the total for each person, I would get 3 for Mike and 5 for Anna. Like KStream, Ktable is a record stream, but if I were to draw the same parallel with a database, records can be inserted, updated, and deleted whenever the value is set to null. Best use for Ktable is to keep only the last relevant data. For example, the total amount for a bank account or the total number of clicks performed by a user. To better understand the differences between KStream and Ktable, you can imagine KStream being a changelog for Ktable and Ktable being a snapshot in time with latest values for each key within a KStream. This leads us to the fact that in Kafka, we have, in Kafka streams, we have stateless and stateful operations. For stateless operations, the results depends only on the input value. So for the same input, we will always get the same output. In this example, we have a transformation that doubles the value for each record. For stateful operations, the results depends on past input values. As you can see in this example, the number of clicks is counted with each record. Before going into true transformations, you can think of Kafka streams as the equivalent of Java streams. And as with Java streams, instead of putting the goodies from the library to work for us, you can use iterators or for loops to go to data. In the same way, you can use Kafka connectors and Kafka consumers and producers to go to data instead of using Kafka streams library. But that wouldn't be so efficient, right? So with this analogy in mind, I would like to go further and talk about the most commonly used operations in Kafka streams. Branch. So this operation performs a split on a stream into one or more streams based on a supplied predicate. We will use this later in the trading example, along with a filter which narrows down the streams based on a criteria. Of course, there is a filter not operation that does the opposite of filter. Flat map takes one record and produces 0, 1, or more records, and in the process, the record's keys, values, and types can be altered. You can see that there are some similarities between the functions in Java streams and those from Kafka streams. So I'll go further with the map, which takes one record and produces one record. Of course, the record's key, value, and type can be altered in the process also. Another commonly used stateless function is group by, which groups records into substream based on a provided key. As I said earlier, in Kafka streams, there are stateful operations that depend on past values, and aggregate is one of the operations that combine values of records grouped by key. Of course, the results can have different types depending on the aggregation operation. Join transformation works like a database table join, and of course, there is inner join, outer join, and left join. This one being the inner join, which produces a record only if both streams have the same key. Of course, there are some variations on this definition, depending on which type of streams we're trying to join, either a K-stream with another K-stream or a K-stream with a K-table, and so on. Another useful operation is count, which counts the number of records by the grouped key. There are many other operations available in Kafka streams, but these are some of the most used ones. Another interesting topic is windowing. Windowing allows us to bucket stateful operations by time, without which our aggregation would endlessly accumulate. A window gives us a snapshot of an aggregate within a given time frame and can be set as hopping, tumbling, session, or sliding. The hopping window is bound by time. It has a fixed window size and a fixed advanced by. As you can see, you could end up with overlapping windows, meaning the records can belong to more than one window. A tumbling window is a special type of hopping window with an advanced size equals to the window size. This means that a record will be part of only one window. The session window is not time-driven. This means that the boundaries are determined by the events themselves. So with session windows, you must define the inactivity gap. So basically, as long as a record comes in within the inactivity gap, the session keeps growing. Pretty much similar to a browsing session. The sliding window is similar to a hopping or a tumbling window in the way that it has a fixed size, but instead of being driven by time, it's driven by events. Now that we covered the basic of Kafka streams, let's view some of the pros and cons of integrating it with Spring Boot. The most important benefit is that Spring Boot creates and configures the required components for the topology and executes the Kafka streams application. This allows us to focus on the core business rather than the application lifecycle. Also, Spring provides a Jackson-based JSON third days serializer, deserializers that can come in handy if we're working on a standalone application. Kafka Streams exposes some of the metrics via micrometer, which is a good way to monitor your application in production. Spring provides some implementations for error handling mechanisms with different strategies that can be applied in your application. The cons of using Kafka Streams with Spring Boot revolves mostly around the generic Spring Boot disadvantages. Developers need to have some knowledge of Spring Boot framework. And of course, there is always that dependency list that increases the deployment file size. Having that said, we can go further and take a look into the only configuration class needed to integrate Kafka Streams into Spring Boot. And for this configuration class, we need to use enable Kafka and enable Kafka Streams annotations to create a bean. Annotation and create a bean for Kafka Streams configuration. For the configuration, we must define the application ID, bootstrap servers, the default surveys for keys and values. And that's it. We can use Kafka Streams pipelines in our application, as we will do in the next trading application example. So what I discovered so far is that data streams have become a must-have resource for trading markets that are highly fluctuating, and there are millions of transactions happening every hour. And this changing values requires platforms that enable real-time data processing to make the right business decisions. Creating an event streaming platform that is highly reliable and scalable and that could ingest millions of orders per second, support high volume of and high-speed trading, provide clients with access to real-time data, is one of the best use cases that I found so far for Kafka Streams. So what is the request? The request is to create a simple application that processes orders and checks their validity. Also, update order prices when they are set to market price by taking into consideration the order type and price spread. The price spread translates in large terms to transactions costs or the broker's margin that varies on multiple factors. As you can see, we have three topics. One for stock price, which contains records, having a string key and a double value. One for stock spread, which contains the same string key and double value for the spread percentage, and one for orders, which contains records defined by a string key and an order object that has an user ID, market price flag, price, quantity, status, and type. We should start by defining a new component that's called order processor, or whatever you want it to be called, with a build pipeline method that takes in a stream builder, an order survey, and a price survey. Being auto-wired, this will be provided by the Spring framework, so we don't have to worry about initializing them. The surveys, of course, are defined, in this case, in the configuration file. So we want to read prices and spread streams into K tables. As we don't care about the entire changelog, we're only interested in having the latest values. So we're doing that on lines 9 and 11. Next, we want to join the prices stream with the spread stream and create a new K-table stream containing a new type of object that has the original price value, the price value for the long transactions, for the long orders, and price value for the short orders. The code for this operation is pretty straightforward. We take the prices value stream and joining it with the spreads values stream by passing a lambda function to the join method, which expects an instance of the value joiner functional interface. In the lambda, we create, initialize, and return the price object. As you can see, the long price is set to price value plus half of the spread, and the short price is set to the price value minus half of the spread. Next, we're going to read the orders from the orders input topic into KStream by using the string serde for the records key and order serde for the records value. Now we're going to filter that KStream for invalid orders, then split it into two branches. One for orders that need their prices to be set at market values, and one default branch for the other orders. Again, the code for this operation is pretty simple. First, we filter for invalid orders, then we split the stream and set a prefix for the branch's name. In this case, it will be orders. After that, we create a branch based on the market price flag using a predicate to separate the orders and, of course, set a name for the branch. And in the end, setting the default branch where the other orders will go into. Now we have two order streams that will be merged in the end. But first, we want to apply different transformations for each of them. For one of them, we want to join the orders at the market price KStream with the K-table prices generated from the previous operation. This should result in a new orders output KStream. The code for this operation consists of getting the KStream from the orders market price branch and joining it with prices, again by passing a lambda function which takes in the order and price objects, sets the orders price based on the orders types, and returns the order. Also, it sets the order status to open. In the final step, we get the KStream from orders default branch, apply a simple transformation on all records values by setting the order status to open, and merge it with the stream resulted from the previous operation. After that, we send all of them to orders output topic using the string serde for the records key and order serde for the record value. That's it. In 50 lines of code, we managed to fulfill our request. Of course, I didn't count the additional imports or use methods, objects, or serdes, but you can see how easy it is to write a piece of code that solves a rather intricate problem. We have some time left. So what about a scenario where we want to count this order stock quantities within an hour? This is going to be a bit more interesting. We take the orders KStream and we'll group them by the same key. Then we will window that stream using a tumbling window with a size of 1 hour. After that, we aggregate the results and sum up the quantities for each stock. The stock name is the key. So next, we transform the resulting K table with windowed records to a stream. And because we want to send to the final topic only the keys and the quantities, we will extract the key from the windowed key using a map function. And with this last example, I hope I got your interest in digging a little more onto Kafka streams with Spring Boot. There are many other use cases where Kafka streams can fit in, but as you can see, it's usually used to enrich data, perform transformations, filter data, monitoring, and in so many domains like banking, insurances, and government agencies, it's used to detect and prevent frauds. Also, another common use case is to scale up your resources by streaming all messages from a topic to another topic that has the desired number of partitions and replicas. So Now we know that Kafka Streams with Spring Boot comes packed with features that can speed up the development process and make it easy to keep the focus on the business rather than the tools. And please consider using Kafka Streams with Spring Boot whenever the project requires high volume and real-time data processing. Thank you.
Do we have any questions? So, questions? If not, I have some. But let's just give everyone maybe half a minute to think. Yeah, so my two questions, you somehow answered half of one of it while seeing the applications, but of course there are some applications where using this approach is beneficial. Have you encountered any limitations with it?
Yes. So Kafka Streams, I think the biggest limitation is that actually it's not a limitation. It's mostly it has its own purpose. Mm-hmm. So either with consumers, if you're using consumers, the example in Kafka Streams, you can use batches. So this is how I see it. And not only that, it can link to multiple servers. Mm-hmm. As with the Kafka Streams, you're processing one message at a time, but this gives that the Kafka that edge of processing real-time mm-hmm. messages. So yeah. This is pretty much the only limitation that I see it in Kafka Streams, the okay. batching size.
Thank you. And I'll also put the second question if I see no hand up. I see a hand up there. So maybe we can have a microphone.
With Kafka, basically, you get consistency guarantees only at shard level. Only at one shard, you get guarantees for ordering and consistency. I'm wondering if you ever ran into issues regarding consistency, and especially into issues maybe when things were, when there were issues like the cluster was not behaving well, like maybe one of the servers or one of the brokers was dying.
No, I didn't encounter that, but you know, you have multiple replicas within Kafka, and Kafka Streams pretty much links to one of them. I didn't encounter, so yeah, I cannot answer that.
But I'm wondering what steps are you taking in order to ensure consistency, or do you feel that if Kafka is a suitable solution for systems where you need a high degree of data consistency?
There are the transactions, which in Kafka Streams are pretty much out of the box. But if you want to go with consumers, you can use your own transactions to make sure that all the data stays consistent across all the replicas and all the... I'm not sure if...
Makes sense, thanks.
We have one more here.
One question in relation with Confluent. Did you feel the need to use Confluent tools, software, in addition to pure Kafka?
Well, it does help. Yeah, they have a lot of great tools. I didn't use any of them, so I work with just the free stuff, let's say. So yeah, Confluent gives a wide range of tools to monitor and have everything, well, speed up the process, right? To bootstrap your projects, let's say, and not only the projects, the entire deployment process. But no, I didn't use any of them.
Good to know, because they promote themselves very, very much.
Yeah, yeah.
Looks like anybody cannot do Kafka without Confluent.
Well, you can do it. You just need to work a little bit more into the deployment and the entire, into the deployment phase.
Thank you.
Welcome.
Any more questions? I'll have just one more, and then we can wrap it up. So, what would be the best resource you'd recommend for someone who'd like to start with Kafka? What would be the go-to?
Well, you can start with the, ironically, the Confluent pages. They offer like a lot of tutorials. They have a lot of information in there. Also, there are a lot of courses within Udemy, Pluralsight, and stuff like this. There are a lot of information in there. You can start very easily with working with Kafka.